My name is Jonas Urbanas. I am a Senior Product Engineer at Mori Microwave, and today I would like to present to you a Vertigo millimeter wave active load pool solution that can be configured to perform active vector receiver load pool measurements up to 1.1 THz. The use of millimeter wave frequencies and millimeter wave active devices has seen a substantial increase in recent years, and they find applications in many different fields such as radio astronomy, radar, telecommunications, and others. The performance of these millimeter wave transistors operating at and above 100 GHz can be highly dependent on the load impedance that is being presented to them. Moreover, the gain of such transistors is generally quite low, as they're operating close to their FT or Fmax values, so an increase of even 1/10 of a dB in gain or an extra percentage point in device efficiency can mean a substantial overall performance gain for the semiconductor technology. Therefore, to quantify a transistor's dependence on its load impedance, active load pool measurements have to be performed, and that is exactly what Vertigo millimeter wave active load pool solution is configured to do. It allows us to actively present various load impedances to our device under test and measure all the parameters associated with the device performance, such as power gain, output power, power added efficiency, and others. The setup as shown here consists of two Rhodian-Schwarz frequency extenders, a Rhodian-Schwarz ZNA, a Vertigo vector modulation unit, a PXI chassis, an AMCAD PAV system to provide the device biasing, and finally the entire setup is powered by the Vertigo mmW-STUDIO software suite. The ZNA is configured to perform measurements of the incident and reflected waves of the device under test, both on its input and output. The vector modulation unit is used to control the input power injected to the device under test, and both power and phase of the signal injected back towards the output of the DUT, which enables the synthesis of the desired load impedance. The signal control is performed by employing two 24-bit PXI digital to analog converter cards that are stored in the PXI chassis. The two cards generate highly accurate I and Q signals that are injected into the vector modulation unit, where the RF signal from the ZNA is modulated in both amplitude and phase, and then injected to the frequency extender units. This enables the accurate power and phase control that are needed to perform load pull and power sweep measurements using the frequency extenders. So now that we know how the system works, we can configure the device measurement in mmW-STUDIO.
Before we measure our device, we need to configure the setup. To do that, we need to start the mmW-STUDIO software suite. Then we can configure our GPIB interface depending on which VESA library is available to us. Once the GPIB interface is configured, we need to scan for the instruments connected to our PC that will be used during the load pool measurement. For that, we go to Instruments, GPIB Serial Analyzer, and wait until the software automatically finds the connected instruments. When the GPIB Analyzer window opens, we can see that on the left-hand side we have a list of instruments that are connected to our GPIB interface. On the right-hand side of this window, we can see the instruments configuration panel, where we need to specify the address of our network analyzer, power meter that will be used for power calibration, DT biasing instrument controls, where we can specify the instrument address and the unit that is used to bias our device under test. And then finally, we have the load pool hardware control section, where we specify the PXI cards used in this setup. Once the setup is configured as required, we can save the instrument configuration file. This will ensure that the system remembers the current configuration the next time we run the software. After we close the GPIB Analyzer window, the instruments will be initialized automatically. The second step is for us to configure the system itself for load pool measurements. To do that, we select System Configuration in the main menu and click Next. A configuration panel opens up where we can specify whether we are using the system in a standard millimeter wave configuration just by employing the frequency extenders, or if a Vertigo vector modulation unit is also used. Then we specify whether we will be performing 1-port or 2-port measurements. And finally, we need to configure our frequency extenders. In the port configuration section, we can specify whether we are using the same frequency extenders on both the input and the output by clicking coupled. This will ensure that the settings applied to port 1 will be automatically propagated to port 2. In the port configuration section, we need to specify the local oscillator power that needs to be injected into the frequency extenders, the desired intermediate frequency, waveguide flange, in this case we are using WR6 frequency extenders, and then we can customize the RF and LO harmonic multiplication factor, and minimum and maximum operating frequencies. When we have finished configuring the system, we click Done. The next step is to select the measurement frequencies. For that, we need to go to the frequency section option in the main menu. Here we specify the start and stop frequencies and the number of points in that frequency range. After we have made our selection, we can click Done. The following step is the system calibration. Here, two-tier calibration is performed, one at the waveguide plane and one at the on-wafer plane. We start by performing a calibration at the waveguide plane. In this case, we will be using a through-reflect line calibration, although line-reflect match is also possible. In the TRL calibration window, we can load error terms if we have already calibrated the system using WinCal. We can change the normalization impedance if the line impedance of the TRL kit is not 50 ohms or we want to change the system's reference impedance. We can modify the parameters of our calibration standards. And we can specify the IF frequency used for the calibration. Now we can measure our calibration standards. When the calibration is done, a calibration results check window pops up where we can inspect the quality of our calibration. Also, we can run a calibration test to see if we are satisfied with our calibration. If the calibration is acceptable, we can move on to the power calibration. For power calibration, we will need to configure the power meter and connect it to the output of the frequency extender on port 1. Then we can click on Perform Power Calibration. The second step that we need to do for power calibration is power leveling. Because the frequency extenders are highly nonlinear, we need to characterize that nonlinearity so we could perform the power sweep measurements and apply power control to the S parameter extraction. In the start and stop boxes, we type in the start and stop voltage values that will be applied to our IQ modulators in the vector modulation unit. We then also need to specify the desired step size for accurate characterization of the frequency extender turn-on characteristics. Now we can perform power leveling. After the power leveling, we see a window with the turn-on characteristics of both the input and output frequency extenders. This information will be used during load pull and power-controlled S-parameter measurements. Now the last thing we need to do is to perform a second-tier calibration at the on-wafer plane. In this case, I will be using an LRM calibration. Just as for the first-tier calibration, we need to change the standard parameters so we can perform accurate on-wafer calibration. When the standard parameters are correctly configured, we can perform the calibration itself. When the calibration is finished, we can test its quality, and if we are satisfied with it, we can proceed with the load pull measurements of an actual device. To perform a load pull measurement, we select the DUT measurement option in the main menu and click Next. A DUT measurement selection window shows up, where we need to select whether we are performing a power-controlled S parameter or a large signal measurement. As we want to perform load pull measurements, we will be selecting the large signal option. Now we need to configure our load pull measurement. First, we type in the name of the measurement. Then we select whether we will be doing just a power sweep measurement without controlling impedances, or if we want to perform an actual load pull measurement where the device load terminations are varied in a predefined pattern for every input power level. After that, we need to change the frequency at which we will be performing the load pull measurements. Here we can also configure a frequency sweep. In this case, a load pull measurement would be performed for each frequency in the frequency list. In this demonstration, however, I will be performing measurements at 125 GHz only, so I select a single frequency option and type in 125 in the frequency box. After that, we need to configure the power sweep. Again, we can choose a single power point for our measurements or a linear sweep. Since we are interested in the device performance as we drive it into compression, I will choose a linear power sweep option and configure the start and stop power levels as well as the number of power points within the specified power sweep range. Now we can also change the conversion settings to make sure that we are controlling the load impedances accurately. Here we can also change the maximum number of iterations for each impedance point. The increase in the iterations number is needed as we reduce the convergence error, so more iterations will now be required to converge onto the desired load impedance. In this window, we can also configure the software-controlled compliance for the maximum power gain compression, and in this case I will be setting the allowed gain compression to 3 dB. Finally, we need to configure the constellation of impedance states for the load pool measurement. We can do that by clicking on the Build Constellation button and entering the desired values in the appropriate fields. Once that is done, we can click OK and we are taken to the data display window. Here, all the measurement data will be displayed. Before we can perform the load pool measurement, we need to bias our device. For that, we go to Measurement, Bias Settings and bias our device. And once the device is biased correctly, we can start the load pool measurement by clicking on the Measure button. During the measurement, the mmW and Studio load pool software sequentially presents the desired load impedances to our device in the test for each input power level. Once the device performance data is obtained at each impedance state, the software increases the input power and repeats the measurement sequence until the entire power sweep is completed. When the measurement is finished, the results are shown in the data display window. There are two sections on the left-hand side of this window. One is dedicated for the S-parameter measurements, and the other is dedicated for the large signal measurement data. As we have just performed a load pool measurement, we can see it listed in the large signal data section. As we can observe, the device was driven nicely into compression. Now we can plot the load pool contours at the desired gain compression point. First, we will add a new plot by clicking on the green plus icon and selecting a contour plot. Then we specify the device parameter for which we want to plot the contours and specify the desired gain compression value. The data display window gets updated, and now the gain contours are visible at the 2 dB gain compression point. We can also plot the contours for various other parameters as desired.
In summary, the Vertigo mmWave active load pool system is a crucial tool to fully characterize the performance of active devices at frequencies up to 1.1 THz. For more information on this or any other device characterization solution, please visit mmW.com or contact your local field engineer. Thanks for watching.